Good morning, dear students. Today we are going to start the first section of our paper Theory of Equations and Abstract Algebra. Okay. The code for the paper is MTS5B05 Theory of Equations and Abstract Algebra. These are the course outcomes, and we are following two textbooks. This textbook for theory of equation and abstract algebra, we are following this textbook. Okay, now just to go through the syllabus quickly. In theory of equations chapter 2, we are discussing division of polynomials, the remainder theorem, synthetic division, Taylor formula. And chapter 3, algebraic equations, identity theorem, fundamental theorem of algebra, imaginary roots, relation between roots and coefficients. In chapter 4, limits of roots, method to find upper limit of positive roots, limit of for moduli of roots, integral roots, okay, and rational roots. And chapter 5, we are discussing what is the solution of an equation, discussion of solution, irreducible case, solution of biquadratic equation, Ferrari method. Okay. And chapter 6, object of the chapter, the sign of polynomial for small and large value of variables, locating roots of polynomials between two numbers having values of opposite sign, geometrical illustration only, and some corollaries and some examples, and some theorems like Rolle's theorem. And in chapter 11, we are discussing symmetric functions and practical method. Okay. Now come to this, all these consisting of the module 1. Okay. And we have 25 hours, only 25 hours for module 1. And module 2, abstract algebra. And here we have we are discussing the first section is integer modulo n, second one equivalence relation. This is from chapter 1 and this is from chapter 2 actually. And permutation. And from chapter 3 we have group theory, subgroup, etc. All these consist of module 2. And module 3 we are discussing constructing our example group with order up to 6, isomorphism, cyclic groups, permutation groups, and homomorphism. Okay. And as per syllabus, we need 18 hours for this portion. And the last module we are discussing causes, structure of groups, isomorphism theorem, automorphism, and commutating rings, integral domains, finite integral domain, etc. Okay. And these are the reference textbook. Okay. So, in our this semester, actually we are starting with the abstract algebra first. Then after abstract algebra, we will discuss about theory of equation. Okay. So, before going to that, what do you mean by abstract algebra? Actually, abstract algebra is a study of algebraic structures. Okay, now what do you mean by algebraic structure, etc., that we will discuss in our later classes. Okay, so which are the algebraic structure? This is actually the algebraic structure which includes groups, rings, fields, modules, vector spaces, lattices, and algebras. Each of these terms are familiar to you, but the meaning in our mathematics is different. Okay, group, you know what is meant by a group. Okay, a group of people like that. But in algebra, we have another definition for groups. Also, you know what you mean by a ring. Okay, that's not the ring that we wear in our finger. And this is also an algebraic structure, and we will discuss detailedly in our module 2 and module 3. Sorry, module 3 and module 4. Okay, now let's move to our module 2. So we are starting our module 2 So module 2, the first section is integer modulo n. So before going to the section, just recall what is the definition of A congruent to B mod n. I think you have discussed or you have studied this in your first sem, second sem, etc. Okay. Now what is the meaning of A is congruent to B mod n? That means actually A minus B or B minus A is divisible by n. Actually A minus B or difference, that means n divides the difference. That means n divides A minus B or n divides B minus A, etc. Okay. So A congruent to B mod n means n divides A minus B or B minus A. That means A minus B is a multiple of n. That means A minus B equal to Kn. Clear? Hope this definition is clear. A is congruent to B mod n means A minus B is a multiple of n or n divides A minus B or B minus A. Okay. Now we are going to define congruence class of modulo n. Okay. So the definition is, let A and n greater than 0 be integers. Clear? A small letter A and n greater than 0 be integers. Now the set of all integers which have the same remainder as A when divided by n. Once again, the set of all integers which have the same remainder as A when divided by n is called the congruence class of A modulo n. The congruence class of A modulo n, and it is denoted by like this. Okay. A modulo. Okay. Congruent class of A modulo n. Okay. And actually the definition is set of all integers which have same remainder as A when divided by n. Okay. Now that is congruence. A congruent modulo n is equal to set of all x belongs to set such that x is congruent to A mod n. Set of all x belongs to set such that x is congruent to A mod n. So what is the meaning of the set of all integers which are same remainder as A when divided by n? For example, if you consider some 5, okay, and you consider our A as our n as 3. So what is actually, we have to find, for A we have 5, okay, and n we have 3. So by definition, what is congruent class of 5 modulo n? The set of all integers which have same remainder as A when divided by n. So if you consider 5, when 5 divided by 3, the remainder is 2. So you have to consider those integers which have remainder 2 when divided by 3. Which will be the next number? When we divided by 3, remainder is 2. Which is the first number? If you consider 2, when 2 divided by 3, remainder is 2 itself. Okay. Then next number. Then next number. 5. Already we have 5. Then next number. 8. Okay. When 8 divided by 3, we have remainder as 2. Then next number. 11. When 11 divided by 3, we will get remainder 3. Okay, then like this. Okay, this consists of all integers. That means in negative part also. Okay, so I think it is clear. Okay, so by definition, this is equal to congruent A modulo n is equal to set of all x belongs to set such that x is congruent to A modulo n. Okay, x is congruent to A modulo n. So here if you consider this set, if you consider 8, clearly 8 is congruent to 5 mod 3, because 8 is congruent to 5 mod 3. It is clear because 8 minus 5 equal to 3 and 3 is divisible by 3. Okay, or if you take 11, 11 is congruent to 5 mod 3, because 11 minus 5 is equal to 6 and clearly 6 is divisible by 3. Okay. Now the collection of all congruence class modulo n is called the set of integers modulo n. The collection of all congruence class modulo n is called the set of integers modulo n, and it is denoted by Zn. Okay, so collection of all congruent modulo n is called in set of integers modulo n, and it is denoted by Zn. Okay. Now we have one note here. Note is integer modulo a n is equal to b n if and only if a is congruent to b mod n. Okay. For proof, suppose congruence a congruent modulo n is equivalence class. Congruent class of a modulo n is equal to congruent class of b modulo n, and we have to prove that a congruent to b mod n. That means a minus b is equal to multiple of some n. So by definition, congruent class of a modulo n is this one, and congruent class of b is this one, and let x belongs to this set. Okay, congruent class of a mod n. What is the meaning of that? By definition, this means x is congruent to a mod n. That means x is congruent to a mod n means x minus a is a multiple of n. Similarly, x belongs to congruent class of b mod n implies x minus b is a multiple of n. Clear? X belongs to this set, that means this condition holds means we will get this one. So if you mark this as some equation 1 and this as equation 2, if you subtract equation 2 minus 1, okay, so what will happen? In left hand side, x minus b minus x minus a, that is x and minus x cancel, here minus minus a, and here we have minus b, so a minus b in left hand side. And what about the right hand side? K2n minus k1n, that is k2 minus k1n. So here a minus b is a multiple of n, that means a is congruent to b mod n. Clear? Okay, now conversely, suppose that a is congruent to b mod n, that means a minus b is a multiple of n. Now what we have to prove? We have to prove congruent class is equal. Okay. That means for proving two sets A and B are equal, what we have to prove? A equal to B. To prove A equal to B, what we have to prove? We have to prove A is a subset of B, and also we have to prove B is a subset of A. So this is our first step. For this we are taking, we are first proving congruent class of A mod n is a subset of congruent class of B mod n. For proving this, you have to choose some element of this set. That is, let x belongs to congruent class modulo n, and this implies x is congruent to a mod n. That means x minus a equal to some c2 into n. And this implies here we have a minus b is equal to c1n. Suppose you take this as some 3 and this as some 4. What about 3 plus 4? 3, if you add 3 plus 4, what happens? X minus, sorry, a minus b plus x minus a left side. Okay, so this cancel and x minus b equal to c1 plus c2 n. That means x minus b is a multiple of n, that is x is congruent to b mod n implies x belongs to congruent class of B mod n. That means here X belongs to this set. Now we get X belongs to this set. That means congruent class of A mod n is subset of this one. Similarly, we can prove this. From 1 and 2 we get from this 2. From 1, suppose this is some, here we have 4. So here we are marking this as some 5 and this is some 6. From 5 and 6 we have congruent class of A mod n is equal to congruent class of B mod n. Okay. Hope it is clear. Okay. Now you can use some examples. As in our earlier case, if you consider some 5, 3 and this is equal to 8, 3. Because we know that 8 is congruent to 5 mod 3. Okay. So by using this result, congruent class of 5 mod 3 is same as congruent class of 8 mod 3. Okay. So we have sometimes we say that the element of an, the element of this an is a representative of the congruent class. Okay. In each congruent class, an has a unique non-negative representative. Okay. If you consider some 5, 3, already we have discussed some 2, 5, 8 like this, etc. Similarly, we will get negative numbers also. That means there exists a non-negative representative and clearly that is smaller than n. Here we have some 2 and clearly that is smaller than n. Namely, the remainder when a is divided by n. Okay, here we have 2. Okay, this shows that there are exactly n distinct congruent classes modulo n. There exists n distinct congruent class modulo n. Okay, so if when a is divided by, if you take some 5 and 3, then when 5 is divided by 3, what about the remainder obtained when 5 is done? It's the remainder 2. Okay. Now, if you consider any integer z, what will be the remainder obtained when it is divided by 3? It may be 0, it may be 1, it may be 2. Okay. So, that means we have 3 distinct congruent class modulo 3 here. Okay. So, we can easily evaluate congruent class modulo 3, 0 and congruent class of 1, 3 and congruent class of 2. Okay. For example, here we have like this. Okay, and congruent class 0. That is the meaning of that. The remainder obtained is 0. That means when divided by 3, remainder is 0 means multiples of 3. That means this one. And what is the meaning of this one? The remainder obtained when divided by 3 is 1. Okay, that means the numbers when divided by 3 having remainder as 1. 1, 4, 7, 10, etc. like this. And remainder obtained when it is divided by 3 is 2. The numbers are like this. Okay. Now, if you consider the union of this set, this clearly is Z. Okay. And each integer belongs to exactly one congruent class modulo 3. Okay, because remainder is unique. Okay, remainder on division by 3 is unique. So, if this minus 5 is here, then minus 5 can't be here. Okay. So, in general, each integer belongs to a unique congruent class modulo n. Each integer belongs to unique congruent class modulo n. Therefore, we have Zn is actually congruence class 0 n, congruent class 0 n 1, etc. n minus 1 n. Okay, this is our Zn. Okay. So with this, we are concluding our today's section. That's all for today's class. Okay.